Hello friends, so in this video we're going to be covering entropy and the second law of thermodynamics with some examples. So the first thing we have to know about entropy before even defining it is that entropy is a state function. So what we covered in our last video is that a state function is defined as a function who is path independent. So at the end of the day, the only thing that is going to matter is the final condition and the initial condition. And if we take the difference of those two, the final minus initial, that gives us our change in entropy. So here is the definition of entropy, which says that entropy is a measurement of the tendency for energy to disperse. When energy disperses, it's going to reduce the ability to do work. And the reason why is because since the energy is not condensed in a singular molecule, if it disperses, that molecule is gonna, well, not the molecule, but the mixture you have, or the canister of gas that you have, if everything is dispersed, it's gonna be a lot more difficult to make it do work, whether that is PV work or some other kind. And that is essentially what entropy is. If we assume a reversible reaction, which is not a realistic reaction, we can say that the change of entropy, reversible, is going to be equal to the heat absorbed or gained, reversible, because it's all reversible reactions are at equilibrium, and that's going to be divided by temperature, where the temperature is going to be in Kelvin and it's a constant. So this right here is a form of an isothermal process. Because it's only one singular temperature. Iso meaning one, thermal regarding temperature. So here we have an example. And this example, it's about elemental mercury. So what it says is that elemental mercury has a freezing point of negative 38.9 degrees Celsius with a molar enthalpy of fusion of 2.29 kilojoules per mole. And it's asking us to find the entropy change when the system, assuming that we have 50 grams of mercury, freezes at the freezing point that we were given. And I noted the molar mass right here on the side. The molar mass is 200.59 grams per mole. So, what exactly is going on here? Well, if something is freezing, mercury at its elemental form is a liquid. So when a liquid converts, well, rather freezes, it's going to convert into a solid, right? So what does this tell us about the entropy? Well, if entropy is a measurement of the tendency for energy to disperse or spread out, well, a liquid at its molecular form, assuming we have a puddle of mercury, which is super unsafe, the molecules sort of look a bit dispersed. And this is going to be turning into a solid, where the molecules are going to be a lot more packed together. So what exactly is going on here? Well, the molecules are coming together, so therefore we're decreasing in entropy because everything is orderly. And that's probably a definition you've heard of entropy before, that entropy is a measurement of disorder or chaos. And while that is correct, I'd rather use this definition in order to understand it, be able to understand the next section that we're going to be looking at in section 19.3, which is regarding the molecular observations of entropy. So we know that this is going to be a negative change in entropy. Delta S is going to be equal to 0, right? Because we're decreasing in disorder. So now, What we also know is that the change in entropy of our system is given by this equation, which is our Q reversible over T. So now, can we really use this this equation? The answer is yes, because we were not given a temperature that it was beforehand, so we don't know if there's a change in temperature. We just assume that this elemental mercury is already at its freezing point, and we just sort of left it there. So we know T. T was given to us in Celsius. So we have negative 38.9 degrees Celsius, and we need to convert this into Kelvin. So what we do is we add 273.15, and I'll graph my handy calculator for this. So we have 273.15 minus 38.9, and this gives us 234.25 degrees Kelvin. So now, we know our T, we don't know our S, that is our change in S, that is what we're trying to find, but we can find our Q. So next what we have is we have this change in enthalpy of fusion. So what exactly is this saying? Well, this change in enthalpy of fusion, what it's telling us is that for elemental mercury at its original state as a liquid is going to be 2.29 kilojoules per mole. However, what we also know is that when you freeze something, that is going to be an exothermic process. Because what is going to be happening is this puddle right here of elemental mercury is going to be losing energy. It's going to transfer its heat to its surroundings in order to turn to a solid. So now, freezing is the reverse of melting. So therefore, we know that our negative delta HF is equal to negative 2.29 kilojoules per mole. And this is the quantity we'll be using because we're freezing. Okay, so how does this help us? Well, now we need to somehow plug this stuff back in, because we have this quantity, but we need to find Q from said quantity. Our Q is just going to be equal to our molar mass. Well, we're going to convert this 50 to moles, right? Through our molar mass. And then we're going to convert this into joules, because Q is measured in joules. So now we have 50.0 grams of mercury multiplied by 1 mole over 200.59 grams of mercury to convert this into moles. And we need to cancel out these moles. So we obtain negative 2.29 kilojoules per mole. And we need to convert this kilojoules into normal joules. So what we obtain is that we have 1000 joules per 1 kilojoule. Now let's see what we obtain. We get 50 grams times negative 2.29. Oh, sorry. Well, yeah, I'll be multiplying it by 2.29, but actually I'll do it right the first time, so none of you guys gets confused, just in case. So we divide by our grams per our mole to mole ratio. and we obtain negative 570.8 joules. This number we can round it up, well, rather round it down to negative 571 joules. So therefore, our change in entropy of the system is going to be equal to this number, our Q, negative 571 joules per Kelvin, 234.25 degrees Kelvin, and we obtain negative 2.436 joules per Kelvin. And we can round this down to negative 2.44 joules per Kelvin. And that will be our answer. And as we predicted it would be negative because it's freezing. So therefore, the molecules that are dispersed in this liquid, they're going to condense into a solid. So that causes something more orderly, and therefore that is a decrease in disorder, which is our entropy.